Dear students, in this final video we shall learn about asynchronous counters. So asynchronous counters are actually built from flip-flops that we have learned in the previous lecture. But the flip-flop that we will be using today is a different one, and it is something called the JK flip-flop. So I choose the JK flip-flop over here. The outputs Q bar and the signals asynchronous reset, preset, enable and the clock are same as the ones that we had studied for the D flip-flop. The JK are the two inputs, and in order to ensure that the JK flip-flops are used properly in the counters, we have to tie both J and K to 1. So in that case what happens? Let's see. I connect the clock over here. So okay, so it is not yet. Let me increase the clock frequency. So you can see that as I have inserted the clock, the internal state or the internal value stored in the JK flip-flop keeps toggling between 0 and 1. So this itself is a fundamental counter. It counts from 0 to 1 and back to 0. Now we shall be using this principle to create a higher bit counter. So I keep this high, and then what I do, I take the output of Q bar and use this to drive the second flip-flop's clock. Now what is this system? This is called an asynchronous counter or an asynchronous system. Why asynchronous? Because these flip-flops are not in sync. They are actually being driven by different clocks. In fact, the same clock is not driving both the flip-flops. Synchronous counters are those where a single clock drives all the flip-flops, whereas in asynchronous clock all the flip-flops are not driven by the same clock. Okay, so now let's look at the output of this flip-flops, or the counters to be more precise. So I will use something called a splitter over here, which will help us see the outputs properly. So I connect 0 over here, I connect 1 over here, and then I choose to select this output with a bit width of 2. So you see, I can see the bit width over here. As you can see, it starts from 0 0, 0 1, 1 0, 1 1. So you see the count is in the upward direction. I go from 0 to 1 till 2 till 3. That means it's in increasing order. That's why it's called an up counter. And because it is asynchronous, the same clock is not driving all the flip-flops. It's called an asynchronous system. And it's using 2 bits, 2 flip-flops, so we call it in totality a 2-bit asynchronous up counter. Now let me try to show you the waveforms. I use these flags over here. So the first one checks the clock, second one checks the output of the first flip-flop, and third one checks the output of the second flip-flop. Now I look at the diagram and I reset it, and I create a bit higher clock period. So as you can see over here, let me make it a bit fast, and then I shall slow it down. Okay, so let this undergo a few cycles, and then it will be easier for me to explain to you how it works. Alright, so as you can see over here, the F1, which is the clock signal, actually keeps toggling, as you can see, and we define one cycle as the time between one rising edge to the next consecutive rising edge. That's one cycle. But you see the output of the first flip-flop, the first rising edge and the second rising edge is a bit longer. And how much longer? It actually includes 2 clock cycles. So the frequency of the output of the first flip-flop is half of the clock frequency. Now if I try to look at in the same way for the output of the second flip-flop, so 1 clock cycle for the output of this second flip-flop, so one period over here contains 1, 2, 3 and 4. So there are 4 clock cycles in one cycle of the second flip-flop's output. So you see what is happening. My frequency keeps on reducing by a factor of 2 as I go on to higher and higher bits in the counter. So you see what I have achieved over here is something called frequency division. In fact, this is the method using which in variety of electronic circuits, when we have a single frequency source, let's say a 1 gigahertz source, and I want to generate lower frequency clocks like 125 megahertz or 250 megahertz, so I'll be using counters, and corresponding to their location and which bit how much frequency I want, let's say 250 megahertz, I'll be using the second flip-flop output, because that's f by 2 square, f by 4, and based on the nth bit I will have 2 to the power n factor of reduction for the frequency of oscillation. So that's it. You can also make asynchronous down counters by inserting inverters at the edges or at the clock edge inputs. You can insert inverter here and an inverter here, and you will see this working as a down counter. So that's it. Thank you.